Hi there, everyone. Today we're starting on Chapter 10, Analysis of Variance. And despite what the name of the procedure is, we're actually still looking at ways of comparing population means to one another. So in that sense, this is a continuation of the work that we looked at in Chapter 9, where in Chapter 9, we specifically focused on comparing the means of two different populations. So how does ANOVA connect to that? Well, we'll be restricting our attention to something known as single factor ANOVA. And what that means is that we are analyzing data that was obtained in one of two different ways. Either we sampled data from multiple populations, or the data were generated by an experiment consisting of multiple groups. So in this very broad description, what we did in two-sample t-testing falls into this, because in the two-sample t-test or two-sample z-test procedure, we were often comparing two populations or data obtained from two different groups. And so therefore, even though ANOVA can be applied to two-sample settings, we generally reserve it for scenarios where we have more than two groups or more than two populations. So exactly what does this look like? Let's just discuss two hypothetical examples. Say someone wants to do a comparison of the four largest private universities in Texas. And so the researcher decides to take a sample of students from each of the four schools, TCU, SMU, Baylor, and Rice. Here we have four different populations defined to be the student bodies at each of those schools. And so this is an ANOVA setting where we are sampling from four different populations. Or another example may be, say the FDA is evaluating two new drugs used for headache treatment. So they run a trial. Participants in a study are randomly assigned to one of three different groups: drug 1, drug 2, or a placebo group. So here, the ANOVA procedure looks at data in multiple groups, where two groups are defined by the new drugs that have been developed that people are taking, and a third group corresponds to the placebo. But in each case, we have multiple populations or multiple groups, and we want to make comparisons across those. So some terminology that you're likely to come across in ANOVA world is people sometimes use special terminology to describe the populations and how they differ from one another. So you'll often see in ANOVA literature the use of the word factor, and factor is just the independent variable, which in the case of ANOVA is a reference to which population or group membership we are referring to. So if you hear factor, that refers to the collection of different populations or the collection of groups that exist. Whereas if we're trying to refer to a specific population or a specific group in the collection of groups, then we'll talk about a level. So each factor has two or more levels. And a factor also has degrees of freedom associated with it. And the degrees of freedom are just one less than the number of levels. This should also be, somewhat reminiscent of working with the t-distribution, where we subtract one from the sample size. But in this case, we're not subtracting one from a sample size, we're subtracting it from the number of levels, which is the number of different populations or the number of different groups. So in the first hypothetical example that I just described on the previous slide, the factor would be the collection of all universities, at least the four universities mentioned. So combined, they are the factor. Like, how does GPA vary by university? How does GPA vary if we know the factor, versus each specific school represents a specific level of the factor. So TCU is one level, Baylor is another level, Rice is another level. Level here does not refer to any kind of ranking or ordering, it just means a different member of the factor or a different grouping in the factor. And in this example, of course, since there are 4 universities, that means there are 4 levels or 4 factor levels, and so the degrees of freedom would be 1 less than that. In other words, this example would have 3 degrees of freedom. Now, we have to introduce a bit of new notation here. For a single factor ANOVA, the number of populations or the number of treatments, or in other words, also, this is the same as saying the number of levels, is denoted by a capital I. And each population or each treatment is assumed to have a different average. So we denote these by mu sub 1, mu sub 2, all the way through mu sub I for the ith population. And in an ANOVA procedure, what our null hypothesis is that on average, there is no difference between the different populations or the different treatments. So we are saying all the population averages are equal to one another. Now, the alternative is not that they are all different. Take a moment and think about what it means if I want to negate the statement, they are all equal. What do you need to contradict that? Only that there is at least one difference. So what we are saying under the alternative is that there is at least one pair, mu sub I not equal to mu sub j. So under the alternative, it's not necessary that all the populations have different means, only that you can find at least 2 populations that differ from one another. So this is the context in which we want to develop a testing procedure. Now we're going to keep things a little bit simple in that we're going to assume that we collect the same number of observations from each population or each group. So j observations from each of the I populations or groups, which means in total, we have I times j observations being taken. For our data notation, we therefore need 2 different subscripts, subscript I and a subscript j. And you'll see here, usually they're just written next to each other, but if it helps with clarity, you can always stick a comma between the 2 subscripts, so I comma j. But if it's clear from context, we typically don't worry about the comma. So what does this mean? If you see x subscript ij, then it's telling you that that is the jth observation from the ith population or group. So let's get a little bit more specific just to illustrate this to you. Say we're looking at group 1 or population 1. Then the data corresponding to that group would be x11, x12 through x1j. So the first index indicates group membership, and the second index is just a placeholder for where the observation is in sequence of being collected. So group 2 data would be x21, x22 through x2j, and the group I data would be xi1, xi2, all the way through xij. Now for each group, we can calculate summary statistics. For a specific group, the way we denote the group average is x bar, you're used to seeing that for an average, subscript I indicating which group we're referring to, and then a second subscript that's just a dot, a placeholder. So for example, if I look at X bar I dot, what I'm saying is I'm taking all the data in the ith group, and there are j observations like that, and I'm adding them together and then dividing by j. So in other words, what I'm doing here is I'm averaging the j observations in the ith group. We also have notation for the overall mean or the grand mean. So this just means we're taking the average of all the observations across all populations. And we denote that by X bar with 2 dots. So a specific dot in the subscript just tells us we've averaged out, if it's the first dot, we're averaging over groups. If the second index is a dot, we're averaging out over members in a group. If it's both, we're averaging out over everything. So this X bar dot dot, you can either think of it as summing all of the observations together, so across the I groups, j observations in each group, or if you've already gone to the trouble of calculating individual group averages, then you can just average over the I different groups. So depending on the data you have at hand, there are 2 different ways to calculate this. Additionally, for each group, we have a group variance. So here group variances are just denoted S1 squared, S2 squared through SI squared. So these are sample variances, right? We don't know what the population variances are. Those are assumed unknown in this context. But if you look at SI squared, so if we're looking at the ith group, that's just calculated the way you would normally evaluate a sample variance. So you take each observation in that group, subtract the group average from it, square the difference and sum, or of course we have the shortcut formula for sample variance that we've previously calculated, right? Which in this case would be the sum of the squared observations in the group minus the sum of the observations in the group squared over the size of the group. So that would be the shortcut way of calculating the variance, a little bit less tedious most of the time. So for each group, you can just take that group's data, calculate the group-specific average, the group-specific variance, and then we also define a grand mean, grand average, which is the overall average of all the data. Now, the assumptions for implementing ANOVA are the following. Firstly, since we have multiple populations or multiple treatment groups, we assume that we are able to sample independently from each of those populations. Next, we assume that within a specific sample, all the observations were obtained independently of one another as well. So we have 2 levels of independence necessary here. And then finally, we assume that each population or each treatment outcome follows a normal distribution, and we're allowing the groups or the populations to have individual means, mu1 through mu but we are assuming common variance. So again, this has a little bit in common with the 2-sample t-test where we assume equal variance and then we have to pool the variances across the groups. So there'll be some kind of pooling that happens here as well. Now, the intuition around where the test statistic we're going to see comes from lies with the following. If the null hypothesis is true, and you go and calculate all the different group averages, what you would expect is that each of those group averages will be fairly close to the overall average, right? They're all estimates of the same underlying quantity. So they should be close to one another, which means they're all close to their overall average. Where on the other hand, if the null hypothesis is false, that means we should be able to find at least one group average that's in some sense going to be far away from the overall average. So we're looking at whether averages are close to the overall average or whether there's some evidence that something is far away from the overall average. And so the test statistic is therefore based on these differences. Now there are a few steps going into calculating the test statistic. We first calculate a quantity abbreviated as MSTR, and this is just an abbreviation for mean squares of treatment. And this is exactly the idea that I was just describing, because the central quantity here sums over all the groups, and it takes each group-specific average and compares whether it's close to or far away from the overall average. So group average minus overall average, square that difference, and then it just has a factor j over I minus 1. Next, we have a quantity known as MSE, or mean square error, and this is just the average of the group variances. So you sum all the group-specific variances and divide by I, which finally allows us to calculate our test statistic. It's called an F statistic, and it's the ratio of MS treatment over MS error. And this follows a new distribution to us in this class, an F distribution with 2 degree of freedom quantities. Nu1 and Nu2, the numerator and denominator degrees of freedom. The numerator degrees of freedom Nu1 is equal to I minus 1. The denominator degrees of freedom is equal to I times j minus 1. And the p-value of the test is then calculated as the probability of having a random variable with an F distribution with those specific degrees of freedom being greater than or equal to the observed F value. Now this F distribution, it's a strictly positive distribution. It's skewed to the right. So if we visualize it, the way we draw chi-square distribution, kind of the same type of figure, and we calculate a quantity F observed, and our p-value is the area to the right of F observed under the curve. The way you're typically going to do that on your calculator, if you have a TI-84 or an Inspire, apologies, let me get back to the correct slide here. You're going to see that you'll have a function called FCDF on your calculator. And this will require you to enter a lower bound of 0, an upper bound of F observed. Degrees of freedom 1 will be your numerator degrees of freedom. Degrees of freedom 2 would be your denominator degrees of freedom. And what I suggested you enter here, that will give you the area to the left. So your p-value would be 1 minus that quantity. And we'll do some examples of F distribution calculations during our live session tomorrow. So to wrap all of this up, we're not going to dig into these quantities too deeply, but instead of working with mean squares, in the literature relating to ANOVA, sometimes quantities are calculated as sum of squares instead of mean squares. Now, the relationships are fairly easy to figure out. There's something called treatment sum of squares or sum of squares for the treatment. This is just equal to I minus 1 times mean square of treatment. Next, we have error sum of squares or sum of squared error. This is related to the mean square error, and you obtain it by multiplying mean square error by I times j minus 1. So you can see those adjustments are just related to the different degrees of freedom. And finally, we have a quantity called total sum of squares, and that is just the sum of the two individual sum of squares quantities. So sum of squares for the treatment plus sum of squares error give us total sum of squares. The reason for calculating this quantity is its value in interpretation. Total sum of squares is a measure of the total variability in the data. So it tells you how much variability in the data exists, but it attributes it to two different components. The variation that is due to the treatment and the variation that is due to random error. So it allows us to decompose the sources of error and see how big each one is. In fact, this allows you to calculate a quantity similar to a correlation value, which we'll dig into a little bit next week. And then the other thing that people sometimes make a big deal of is just how all of these results get reported. Specifically, in a lot of academic disciplines, people like to see them reported in a tabular way, and the way that gets done is we have rows for sources of variation. So whether it's a treatment or error or total, each of those has degrees of freedom. So we already established treatment has I minus 1 degrees of freedom. Error has I times j minus 1 degrees of freedom. And if you sum those, you're going to get total degrees of freedom. So if you sum those quantities, you'll get I times j minus 1. Similarly, we just define the sum of squares quantities, and sum of squares for the treatment and sum of squares error should add up to sum of squares total. Now at this point, we can report the mean squares. We can work backwards now, right, and just say mean square of treatment is sum of square treatment divided by I minus 1. So it's just the sum of squares divided by the degrees of freedom, and sum of squares for the error divided by degrees of freedom. We do not calculate a total mean squares. And finally, we have our F observed, which is the ratio of the two mean square values for treatment and error. And so we will dig in and do a few examples tomorrow so that you can see how all of this hinges together and how we can reach conclusions in experiments with multiple populations or multiple groups.